Hello, uh, welcome to J4K and to my session on transactions for microservices. Those of you who've been to any of my presentations over the last 20, 30 years will know that transactions is something that's very dear to my heart. And with J4K, I got the opportunity to talk a little bit more about it, which I tend not to do in my main day job. So let's start with some, hopefully some things that are not a surprise to this audience, but realities of distributed systems. Machines and software fail. If you've ever done thermodynamics, you will know that one of the laws of thermodynamics is that entropy increases, and essentially, to put it bluntly, and pardon my use of language, but shit happens. Things just keep failing. Obviously, things failing today are, they tend to fail a lot less than they did 20, 30, 40 years ago, but stuff still does fail. It's, it's inevitable. And failures of centralized systems are very difficult to handle, but at least if a centralized system crashes, it all goes down. Failures of a distributed system are much more difficult. In fact, one of the oft quoted definitions of a distributed system is where the failure of a machine you've never even heard of, probably in a place you can't even get to, causes your application to not be able to make forward progress. And our move to microservices and to cloud-based environments like Kubernetes is all about distributed systems. And hopefully you'll see from this presentation that there's still a lot that we can learn from the past to hopefully help us not make the same kind of mistakes that we've made when we move forward with microservices as we're doing today. So in that vein, and apologies for the slightly grainy look of this, but I did want to cast back to 2014, so 8 years ago. When microservices were really starting to be talked a lot about. And Adrian Cockcroft, who I believe at that point was still at Amazon, he was like chief architect of Netflix prior to that, I believe. He's one of the people who's often credited with coining the term microservices. And even he admitted back then that his term really meant more of a fine-grained service-oriented architecture. And as we'll see, there's a lot that we can learn from, good and bad, from SOA. Now, if things fail, then we need some mechanisms to try and tolerate those failures. And broadly speaking, there are a couple of categories. And there's replicating of those resources to increase availability. So, if you've got 3 or 4 versions of something running, failure of one, hopefully with a suitable replication protocol, you can tolerate that and keep going. And there are different approaches to replication. There are passive replication, active replication, but they all tend to try and guarantee forward progress. And it's guarantee in quotes because there are always assumptions. You could have a catastrophic failure that takes down every single replica. And despite the fact that the probability may be low, it's still not zero. One of the nice things about some replication protocols is that if you don't have to have identical copies in terms of implementation language or even implementation algorithm, as long as they conform to the same API, you could have one implemented in Java, you could have another one implemented in JavaScript or Rust, and like I said, you could use different algorithms for getting the same kind of results. The other category is what was originally termed spheres of control, and one of the probably the most popular approach to spheres of control are transactions. Spheres of control, as kind of, hopefully the name kind of implies, are a unit of work, and within that unit of work, all of that work happens or none of it happens in the presence of failures and concurrent access. Like I said, transactions, which many people hopefully are aware of in relational databases, are an implementation of that. But what is a transaction? Broadly speaking, it's a mechanistic aid to achieving correctness. As I said, it provides us all or nothing capability. So you do work, and if a sphere of control or a transaction in this example has to roll back or fails, then all of that work gets undone. There's no partial undo, and that happens even in the presence of failures and concurrent access. And it's a really good mechanistic aid for building applications in general and distributed applications. And as I said here, it tries to guarantee the notion of shared global consensus, like like I was saying earlier, everything happens or nothing happens. The typical transaction implementation that you may have heard of is what's known as ACID transactions. So you have this atomicity, everything happens or nothing happens. Consistency, so the system moves from one consistent state to another consistent state. Isolation, so in the presence of multiple concurrent access to some shared resource that's being modified within the scope of transactions, we guarantee a level of isolation, so concurrency control, for instance. And there are different levels of isolation. And then durability. So all of the state changes that happen in a transaction are made persistent. This is how we get this fault tolerance capability in the event of failures. One of the interesting things, and perhaps not everybody is aware of this, that although transactional systems, and there are a number of them in the world, they've been around, many of them have been around for a long time, although they will work to guarantee the A, the I, and the D, the consistency aspect is really pushed to the application level. There's nothing that a transaction manager can do to ensure consistency. It's assumed that the application moves the state of an object, for instance, from one consistent state to another consistent state. So what about using ACID transactions in microservices? They've been around for a long, long time, 40, 50 years in one way or another. And certainly in the Java world, if you've been using Java application services or Spring Framework, for instance, you'll be well aware of JTA. And as I said, if you're using relational databases, you'll be well aware of ACID transactions. And prior to J2E, there was there is a standard from the XOpen standards body called XA. JTA essentially tries to map to that. So ACID, like I said, ACID transactions have been used for a long, long time. So the obvious question is, why not use them for microservices? Now, the reason for this is ACID transactions, they implicitly assume a closely coupled environment, and that transactions or these spheres of control are only operating for a very short duration of time, milliseconds, seconds at most. Therefore, they don't really work well in loosely coupled environments where activities are going on for a long, long time, whether it's tens of minutes, hours, days, or even longer. The assumptions that go behind ACID transactions tend to break down at that kind of level. But hopefully we're well aware that microservice-based systems are very, very complex. As I said earlier, distributed systems are complex. So they typically involve multiple parties, multiple microservices. They can span multiple different organizations, even in the same company. Lots of companies are grouped into different organizations, and you can have microservicing applications that span one organization to another, and they can last many, many minutes. And in that kind of case, the isolation capability that we get for ACID transactions, which is typically driven by grabbing a lock on something, you can't really afford to lock that resource on behalf of an individual microservice or user for a long time, potentially indefinitely. And also, you might want to kind of relax that ACID capability. You might not be able to, or even want, in the event of a failure, to undo absolutely everything that's happened, especially if, as I said, these things are running for minutes or hours. It might be okay to, in the event of a failure, to only undo some of that work. So these are problems that have actually existed for decades, not long after ACID transactions came out. In fact, if you are able to get a hold of a paper by Jim Gray, who was at IBM at the time, and he wrote one of the very first papers on ACID transactions, in his appendix of that paper, he even talks about relaxing the ACID capabilities. And over the years, there have been an awful lot of what are now termed extended transaction models to try and provide spheres of control implementations that better map to these kind of requirements, predating microservices. But these problems that we see with microservices and service-oriented architecture before it, and other implementations prior to that, have been around for a long, long time. And here's just a few of them. I'm not going to call them out. Hopefully you can get access to the slides later on, and you can maybe go and look at some of these. And importantly, there are some other standards in this space. So I mentioned XA for ACID transactions, but there are various standards bodies that have been doing work in this area for extended transactions for a while. OASIS and even the OMG and the JCP. So there was a JSR that span up, I think it was the late 90s. I was actually leading it at the time, JSR 95, pretty sure it was 95. You can go and have a look at that. I just want to put this in because this was me. If nobody can recognize me, I'm the guy with the funny hat on the right-hand side at one of the OMG standards bodies back in the late 90s, where we were working on standardizing one of these extended transaction approaches. And I just wanted to put this in here to two reasons. One, to illustrate that a lot of this work has been going on for a long, long time. But two, just for those people who think that transactions are pretty boring and dull, we know how to party as well, okay? So I just thought this was a really nice slide to show that, we can have our wild moments. So all of these works on extended transactions, as I've kind of hinted, attempt to try and relax one or more of the ACID properties. So relaxing isolation, I kind of mentioned a little bit of this already, but the isolation capabilities that an object has could actually be down to that implementation, rather than decide I'm only going to allow multiple readers and a single writer, which is the typical serialization mechanism that ACID transactions tend to have. You could, if you, as an implementation, you could decide to have multiple writers and multiple readers. It does impact applications though, because then you could potentially, in the event of failure, have notions of dirty state or stale state. Relational databases have been handling this in one way or another for a while, so this is not something that is hopefully new to many people on this call. But in this case, if a sphere of control is working in a manner that is allowing relaxation of isolation, and it decides or it fails, or it decides to roll back or cancel, then the undo of that action could be up to the implementation. How do you move from one consistent state to another? As I said, with transactions, that's not something that the transaction manager does. It's up to the application anyway, but it's driven by the transaction to say, I am rolling back, go back to your old state. And typically it's done with a before image and an after image. That could be very different if you're relaxing isolation. You could actually be firing up a completely different business process to forward compensate rather than reverse compensate. Relaxing atomicity, as I mentioned before, particularly in long-running interactions, you may decide that you don't want to cancel all of the work in the event of a rollback or a cancellation. It may be possible to take a chance. I booked my flight, I booked my hotel, but I couldn't get my taxi. You know what? I want to keep the hotel and the airplane flight, and I'm gonna walk to the airport or gamble on an Uber or maybe call a friend to take me. There is a transaction model that's been around since '84. Elliot Moss, if you want a reference to that paper, defines something called nested transactions. And that allows you to have, as its name implies, kind of multiple nesting of ACID transactions, but each nest, unless you're a top level transaction, you don't have the full ACID capabilities. Work performed within the scope of a nested transaction is actually provisional on the enclosing transaction committing, and again, all the way up to the top. But it's actually a pretty good scoping mechanism, and it works really well for modularity. Then we, then we have the relaxation of consistency. Kind of touched on this a little bit with ACID transactions, strong consistency or global consistency, but that tends not to scale. Replication researchers have probably been pushing the envelope on weak consistency for a lot longer than some in the transaction field. I did my PhD on replication and transaction back in the early 90s, and back then it was kind of it was cutting edge research to talk about weak consistency. We weren't even talking about really large scale back in those days, but weak consistency was something that was recognized as being an area that was going to grow in importance. Now I think you just have to look at the literature of products, let alone relevant recent research, and you'll see lots of groups talking about weak or relaxed consistency, eventual consistency. So there are a number of those extended transaction models I presented earlier that touch on this and allow it to happen in, or try and allow it to happen in a controlled manner. However, almost like the isolation thing we touched on earlier, it is something that you need to be aware of. In fact, even with the relaxation of atomicity, as an application developer, you need to be aware of it, because if you're not, it can take you by surprise. So that's, as I said, that's kind of relaxation of one or more of the ACID properties. You could actually, if you think about it, structure your transactional applications from short duration ACID transactions. And one of the extended transaction models I mentioned or had on the slide previously, called sagas, is an example of that, where essentially, as you see the diagram here, you have the big ellipse, which is the work you want to get done. Ideally, booking a taxi, reserving a restaurant, and a theater and a hotel. And this is going to span, let's say, hours. If you did that within an ACID transaction, you'd have all the problems that we mentioned earlier about having to keep locks for a long duration. And if it crashed just after this LRA4 thing, you'd have to roll back everything and start again. So you could have each one of these things, the booking, the taxi, the restaurant, the theater, and the hotel, as separate, shorter duration transactions, and then group them together somehow. Now, a transactional workflow system would be ideal for doing this, but there are other ways that you could do it. You could do it in your application and become responsible for ensuring where your application is in the the trajectory of going from booking the taxi to the final thing, which is booking the hotel. So you might think that what I'm suggesting is don't use ACID transactions, or if you do, use them in a this short duration manner that I mentioned earlier. And if you've been in this area for a while, you may remember that some of the more prominent early work on weak consistency and extended transactions was actually driven by work that Google was doing. But about 10 years ago now, it's hard and in some ways shocking to think it's almost 10 years ago, Google kind of did an about face. They released a paper about a system they've been working on called Spanner. And Spanner is all about ACID transactions and strong consistency. And this is a quote from the Spanner paper. I tried to put a reference in here, OSDI 2012. If you Google that, you should hopefully find that paper. But essentially, they decided that the overhead of actually looking for and fixing performance bottlenecks in applications because they're using ACID transactions is worth it compared to the issues that they've found with weak consistency or eventual consistency. So I think in some ways this actually shows something that I also want to mention, which is that one size doesn't always fit all. There are many of those extended transaction models, and you will find that they're all use case driven. So some are good for some use cases, some are good for others. And unlike people have tried to use ACID transactions for lots of different things, and that's caused problems in the past. So You wouldn't do the same with extended transactions. You wouldn't use Sagas to address every single use case, for instance. So where does this fit into the Kube-native world that we're in today, and very specifically because this is JFK for Java? Well, I'm pleased to say that a lot of the work I mentioned earlier that's been going on in Oasis and OMG, and appearing in various vendor implementations, and also upstream in a few open source projects. A lot of that has been feeding into the Eclipse micro profile community efforts. And a few years back, this thing called long-running actions was created. And version 1 is out now. It's actually based on one of the standards that I mentioned earlier, or briefly mentioned earlier, at Oasis. So Oasis WS-CAF had within it an extended transaction model called long-running actions, and this kind of leverages that or builds on that. There was some similar work going on in the Oasis WSTX effort, but primarily this is long-running actions, and it's very similar to Sagas. So as the slide says, in this the assumption is that your business process is split into smaller business tasks, these activities, the smaller spheres that we saw, or ellipses, sorry, that we saw earlier on the slide. And as you progress, the long-running action implementation coordinates how you go from one activity to another, and in the event of an activity failure, it uses forward compensation. So this, like I said, this is the kind of the Saga model. So an activity gets triggered and is told a participant in an activity gets triggered until this activity is going to cancel. You need to do some work to try and return yourself to the state that existed prior to the activity beginning. So LRA, like pretty much all of the microprofile specifications, is heavily annotation driven. So CDI has been a core component of microprofile from the beginning, and these are the annotations that it has. So you've got compensate and complete and forget and leave. So I won't go through each of these. You can go and have a look at the spec yourself, but leave, I will focus a little bit on leave. So leave, for instance, this allows a participant in an activity to leave that activity before the activity is actually ended. And this gives us the relaxation of atomicity that I talked about earlier. So you can literally say in your application, you know what, I'm at a point now where that work is done, and if this activity is to fail, hopefully it won't fail, but if it is to fail or decides at the programmatic level to cancel, I don't want this work to be canceled. So I'm going to leave now. And it literally does that. It kind of unregisters itself with the LRA. Just conscious of the time. So this is straight out of the LRA specification. So again, you can go and have a look at that. But essentially, it just diagrammatically shows what I talked about earlier. When you have a participant, or a service in this case, joins the LRA, it can add a compensator to that LRA. And when the LRA decides to cancel, in this case, it sends a compensate message to the compensator. And that, in the case of compensator 1, it is meant to return the state of service 1, or the objects, because there could be multiple of them, to a state that is consistent with that service prior to the LRA having begun work on it, or as close as it possibly can. And as I said earlier, that could be firing off a completely different workflow. It could be something that compensate could run for minutes as it undoes. And in fact, that compensate could itself be a long-running action. Here's a quick example, JAX-RS. So REST easy would be an implementation, but obviously other REST implementations are available, as they say. This is taken from, I think this is taken from so Narayana, we'll talk about this in a minute, but I think it's taken from one of the blogs that team have put out. But you can see down here the compensate work method annotated with the compensate. The complete work annotated with complete, that's essentially the thing that gets triggered if the activity is going to finish successfully. You can try all of this out with Quarkus. Hopefully, you all know what Quarkus is by this point. It's been around for a few years. The first Kube-native Java implementation that there has been. I know that there are some Quarkus sessions later on, so hopefully you'll stay around and listen to them. But I put some links on here. Again, if you get the slides, you'll be able to look through them. But these are links to the LRA and LRA guide in Quarkus, but also a blog on actually using LRA with Quarkus. So please take a look at that. But there is more. So I don't have time to go into this in a lot of detail, but Narayana, which is the implementation of LRA that Red Hat provides in Quarkus, also has a software transactional memory implementation. It's Java annotation based. You can define objects and you can have pessimistic and optimistic models. It has a number of different extended transaction models based in it. Obviously, it's got top level ACID. It has nested transactions. It also has something called nested top level. So no matter how deeply nested you might be in a transaction hierarchy, you can fire off a nested top level action, and that immediately goes. And when that finishes, that work is done, and it's not provisional on any closing transactions. And a link here to the guide for software transactional memory in Quarkus, because you can try that out there as well. So in conclusions, transactions and microservices, you might have heard over the years, no, they don't go together. Like we used to hear the same thing for SOA or even for REST, but they kind of do. They just don't necessarily mean the same thing as we might have been thinking about for the 30 years prior to that. The ACID transactions still have a role to play, whether it's in just running short duration interactions as one-offs or the coordinated workflow type style that I mentioned. Absolutely don't rule out using ACID transactions. As I said earlier, Google eventually kind of came back to that. Eclipse Microprofile, I think, is making a good effort to standardize these things for the Java developer. So please get involved there and look at some of the implementations. So Narayana is the one that I would encourage you to look at. Get involved. If you feel that the LRA model is not suitable for your use case, that's fine. As I said, there are lots of extended transaction models that are geared to different use cases, and Microprofile would be a great place to actually bring your experiences and try and standardize something. But I want to try and emphasize this very last bullet. These need to be based on real world use cases. We don't want to get into the business of trying to standardize things that are research projects or just ideas. That's the scope for an upstream community project. That's exactly where open source is really, really good at. But standardizing, you're kind of casting something in stone at that level. And we should only be casting things in stone when we know they're actually right or pretty close to right. And that's where the real world use case comes in. Okay, so thank you very much for listening to me. I will stop sharing so I can look at the questions. So there is one question. How is Kubernetes native different from cloud native? Are they complementary? It's a good question. So these days they're getting closer. So cloud native was a term that was coined before the industry, including public cloud vendors like Amazon and Microsoft started to standardize on Kube. So they back then, and they still do to a degree, they all had different underlying implementations. Amazon AMIs, for instance. These days, each of them probably has, or I know they have, their own Kubernetes implementation as well. So cloud native and Kube-native are becoming similar, but Kube-native is certainly, if you're looking at kind of hybrid cloud, where you want to span multiple different public clouds or even private cloud and public cloud, Kube-native is where you really should be focusing, because Kubernetes becomes like that abstraction layer that allows you to port and run from one implementation to another. And if that's the only question, again, I'll thank you all for listening to me. Hopefully you you found this as entertaining as I did to pull it together. And I will say thank you and goodbye.